Hello everyone, and welcome to this new and exciting session in which we are going to treat transfer learning and fine-tuning. Transfer learning can be applied in several domains like computer vision, natural language processing, and speech. In order to better understand the usefulness of transfer learning, we have to take note that deep learning models work best when given much data. And so this means that if you have a data set of only 100 data points, then you're most likely going to have a poorly performing model. But what if we tell you that it's possible to train your model or to train a given model on, say, 1,000,000 data points, and then use that model or adapt that model such that you can now train it on this your very small data set such that you start getting very great results. This is very possible with transfer learning, and that's what we shall be treating in this section. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. At this point, one question which may be going through your mind is, how is it possible to train a model made of, say, 1,000,000 data points and then use that same model on a smaller data set, which is obviously different from this data set, with about 100 data points? The answer to this question lies in this figure we have right here. Notice how you have this image here, this image of this truck, and then we have this model which takes this input and then produces some outputs right here. This model, or the kind of model we'll use for this image tasks, are generally the ConvNets, as we've seen already in this course. And with the ConvNets, we generally have two main sections. The first section is the feature extractor. And then as we go towards this final sections here, we have the classifier. And so the very first thing the ConvNet will want to do will be to extract low-level features. And then as we go towards the end, we start or we focus on extracting more high-level features. Notice how here, with this, let's pick out this feature right here, or this feature map. You see that we pick up these edges. You see, for other feature maps, we actually filtering out some low-level features or extracting these low-level features from our input. Then as we get towards the end, we get more high-level features, like for example whole portions of the image, like the tire. And then after this, we generally have a classifier which now permits us to pick between a set of options which one the model thinks this image is actually. Now, because the ConvNet works this way, it means that if we have two data sets which are similar, then we could build some sort of feature extractor, or we could build a model which will extract features from this very large data set. And then because these weights have been tuned or have been trained such that they extract features correctly, then when we pass in this very small data set, this section of the model will do just its job, that is, of extracting useful features from this data set. And you see that because these two data sets are similar, it's going to do a great job. And so we will not need a very large data set in order to extract features from this small 100 size data set right here. And so in fact, what we're saying is we have a model. Let's say we have this model, then we have this feature extractor unit, and then we have this classifier unit, which we've seen already. Generally, this starts after the flattening or the global average pooling, and then here we have some dense layers, while with this we have a convnet or some convolutional layers with some max pool and batch norm layers. So what we're saying now is we have this our small data set which we're going to pass in here, and then we'll get at this point. So it's here that we're going to get this outputs from our feature extractor unit. And then since generally we have, for example, or we pre-trained this model, note the word pre-trained because we are somehow using this for the first time in this course. We are pre-training, or we pre-trained that's we did the training before. We pre-trained the model on a large or relatively large data set, like for example ImageNet. Let's suppose that we pre-train on some large data set with 1 billion images. Then this unit here has learned to extract features from whatever image you give it. And so now when you come with just 100 images, what it does is it extracts those features, and then since at the level of this classifier we have a different setup for the pre-training, we now have to modify this classifier. So this means that if before, let's suppose that before we had after the global pooling we have say 100 unit dense layer and then 1000 output dense layer right here. Then in our case where we have just 3 outputs, what we'll do now is we'll simply replace this here. We'll take all this off, and then now we may pass this say directly to the 3 output dense layer, or we may pass this first to say 128 and then to this 3 output dense layer. So from here we see that this new model will focus more on the classification while allowing the previous pre-trained model to take care of extracting these features from our data. Now it should be noted that we generally use this concept of transfer learning when we have a very small data set, and obviously since deep learning models perform best with large data set, we want to get the best out of them, and so we want to use the transfer learning when we have a small data set, as we've said, and we have this model which has been pre-trained to extract those useful features from those kinds of images. So this simply means that we should have 2 similar data sets. Another advantage of using or working with transfer learning is that you get to gain in terms of training compute cost. That is, this model which was pre-trained may have been trained for say 3 days, and then now all you need to do is just get this pre-trained model and then apply transfer learning on your own specific and smaller task. And so when you're running on limited budget, you find that working with pre-trained models is going to be really helpful. Now, apart from transfer learning, we also have fine tuning, which is quite similar in the sense that unlike with the transfer learning where we have this here, that's this feature extractors weights which are fixed, and then during training we update the weights of this classification section. With fine tuning, what we could do is also update the weights of this feature extractor section. Now generally we start fine tuning from the top, so we suppose that this is the bottom here, so we have the input and then we have this final layer. So we would say that we'll start fine tuning from this final layers going to this initial layers. So here we have this fine tuning process. We could get this top layers, that is, we fix this layers here, we keep these layers fixed so their weights aren't updated during the training process, and then we update these weights. While obviously we update these weights already, but the difference is that these weights were initialized from scratch. That is, we randomly initialized these weights, whereas these weights are initialized from the pre-trained model. Now this weights here are from the pre-trained model, but they are not trained. Now we could, again, depending on the kind of results we're getting, meaning that if we apply fine-tuning to these top layers or to these final layers and we get better results, you see that what we could do is we could keep fine-tuning. So we could keep increasing this section of weights we could update in the feature extractor unit. So here we'll take this off, and now we have this part which we can train. So this is trainable, this is untrainable or not trained. So we have something like this. Now it's also possible for us to go ahead and just say, okay, we're gonna train all our model. But while carrying out fine-tuning, if there's one thing you need to note is that you have to use a very small learning rate. And the reason why you're doing this is to avoid disrupting these weight values which have taken very much time to attain. And so as we do the fine-tuning, we're going to update these weights, but very slowly. And by updating this weight very slowly, we mean we're going to choose a very small learning rate and then observe how this affects our model's performance. At this point, we'll get straight to the code and we'll look at some pre-trained models. So here you could see you get into this TensorFlow applications. You have ConvNext model, DenseNet model, EfficientNet model, EfficientNet v2. We've seen the EfficientNet already. InceptionNet, MobileNet, which we've seen, MobileNet v2, v3, NASNet, and the famous ResNets, which we've seen already with the VGGs and the exception net. So here you have the choice of picking out any one of this. We're gonna go straight to the EfficientNet. So we could have this here, or you could pick the EfficientNet v2. So you could pick any one of this. So here we're gonna pick the EfficientNet b4, this one, since it has slightly fewer number of parameters compared to the ResNet 50, and it outperforms the ResNet 50 by a very large margin. So we're gonna pick this EfficientNet b4. And if there's one thing you can do with TensorFlow is simply the fact that you could use these models without having to code them out from scratch. So as you could see here, we have this TensorFlow keras applications, EfficientNet, EfficientNet b4, and then we just have this argument. With this, we get, we're gonna define our EfficientNet model. We paste this right here and we'll call this the backbone. So we've seen this already. Now here we're not going to include the top. Recall that as we had seen here, we have this whole model, and then let's take this fine-tuning part off. We have this whole model, and then what we are interested is in this feature extractor unit. So we'll set that include top to false. Let's get back here. We have include top. We're not going to include this. We set this to false. Let's take this off. And then the weights have been pre-trained on the ImageNet dataset. We're going to take this input tensor. We have the input shape. Now this input shape will have configuration. So basically we have configuration, the image size, the im size. There we go, im size by configuration. And since we are not including the top, as we've said here, we're not going to take into consideration these classes nor the classifier activation. So we have that off, and then we could decide whether to include the pooling layer or not. And if we want to pick the pooling layer, then we'll have to specify what pooling layer we want to work with, either the average or the max. So with this, we are just going to take this off and specify that later on. So here we have our backbone. We run the cell, and then what we do to freeze, what we call this is freezing. So what we do to freeze this backbone such that the weights aren't updated during training is by simply setting this here to false, or setting this trainable parameter to false. So backbone.trainable equal false, and that's it. So this is all we need to do to freeze our model. Now we've frozen our model. The next thing to do is to add this other layer right here, or this other layers. So we'll go straight away. Then here we're going to define this input with the image size. Now once we have this input, we now pass in, or we have the backbone. So we have the backbone here, which has been defined, and its parameters have been set to be frozen. And then from here we have the global average pooling. So we have global average pooling here. Then we now have this dense layer. Now in the configurations, we set this number of dense layer 1 to 1024, and number of dense layers 2 to 128. So let's get back to this. There we go. We have that, and then from here we're gonna have batch normalization layer. There we go. Let's copy this, paste it out here. We have another dense layer. Now this time around, the second one. That's fine. And then finally we have this dense layer activation softmax. So here we have our softmax activation, and then this is number of classes. Here we have number of classes, and that's fine. So let's take this off now and then run this cell right here. We get in this error because we have to specify this way. That's fine. And that's it. So now we have this model. You see total parameters 19 million, the trainable parameters just 1.9 million, and the non-trainable parameters are 17.6 million. So it means that the backbone itself is 17.6 million, and then this additional parameters here come with the remaining 1.9 million parameters. Now with this, we have our model already set, you see, with minimal code, and we could go ahead to start the training. Then here we can now start by training our model again. We compile the model and we run the training process. Now training is over. We could go ahead and evaluate our model. So let's run this, and what do we get? We have close to 85% accuracy and 95.3% top K accuracy. And this does slightly better than the previous models which we had worked with. Let's go ahead and test this. So we change this to model and we run this here. Incompatible, found shape this. We're gonna resize this before passing into the model. So here we have this image, and just here we have, let's say we have our test image, which will resize. So we'll use OpenCV to resize this image. We pass in our test image, and then we specify this our im size. So here we im size, copy this, and there we go. Let's run this again, and here's what we get. You see, we have the sad output. Now let's go ahead and check this out here. We run this. Here we have one miss. No miss. The second miss. Here we have two misses, and that's it. So out of the 16 we have 2 misses. That is 14 divided by 16. About 87.5% accuracy on this small batch of images which we took from the validation data set. We go ahead and check out the confusion metrics. Oops, let's run this. Let's get back, and here's our confusion metrics. We get even better results. But one thing we have to note here is that our data set was not that small, and so we may not see this change or this difference between training from scratch and using transfer learning. So what we'll do is we'll take this, we'll take just say 10, that's 320. So we'll have a data set of 320 data points, and then we'll see the difference when we train from scratch and when we train with a pre-trained model. So right here, let's get back to this. We take this down, and we could use any of this one. So let's pick the Lunette. It's quite simple. Pick the Lunette, and then here we have in this, let's scroll down, we have training, loss function the same, metrics the same, and here we have Lunette model. So run that, and here Lunette model, that's fine. And so here we'll train on this small part and validate on the full validation data set. We'll do this for just 20 epochs. So after training for 20 epochs on that very small data set, you see the model doesn't perform well. You see it doesn't even get up to 50% validation accuracy, while the train accuracy keeps increasing. So the model is overfitting. Now from here, we are now going to change this. So we're going to use our model, this pre-trained model. So we have this here. We just run this again. So we initialize this parameters, and then we'll compile the model. This is model, so let's call this pre-trained model. Let's change this name here to pre-trained model. There we go. We have pre-trained model, and we get the pre-trained model summary. That's fine. Here we have that, and then here we have pre-trained model. Okay, so here we're gonna run this pre-trained model, compile, and then we'll start with the training again. So just note that we had the accuracy, validation accuracy, below 50% previously, and now we're gonna check out our validation accuracy when working with the pre-trained model. But already, one thing you could notice, just after 2 epochs, like here, see, after this 2 epochs, we are gonna see this validation accuracy, which is already greater than 50. Even from the first epoch, it was already greater than 50. It shows you the power of working with pre-trained models, as we are now making use of those extracted features to get this much more performing model. See how the accuracy keeps increasing. Now we're done with the training. You could see that this model, which before we couldn't cross this 50% mark for the validation accuracy, now is able to cross this mark, as we'll see here. You see we have the validation accuracy of 71% while just training on 320 data points. So let's get here, let's run this, and you could see what we have here. You see it gets just above 70%. So now with pre-training we get above 70%, and we even got greater than 50% just from the very first epoch. And so what we could see from here is the very first thing is get as much cleaned data as possible, and if you can't lay hands on this, try some data augmentation. And then from here, if your data set is still very small, then you could then apply transfer learning. But if you have a relatively large data set, it will be needless applying transfer learning, as training from scratch should normally get you better results. So here we could evaluate our model. So you could see that this is our pre-trained model with just 10 out of 213 batches, which produces 71.3% validation accuracy. We now move on to fine-tuning. That's, we've looked at transfer learning, and now we get into fine-tuning. But before getting to fine-tuning, we would first convert this our code, which was built with the sequential API, now into the functional API. So here's our converted model. It's basically the same thing. We have the input, we have the backbone, which takes in this input, produces output, global average pooling, dense layer, batch norm, dense layer, and this dense layer right here. Then we have our fine-tuned model right here. Let's run this, code cell, and then we could view a summary which is meant to be identical to what we had already with the pre-trained model. So here we have this 17.673 thousand. See, this is 675. It doesn't match with what we expect, so let's get back here, and we'll notice that we did not put this here. So let's X, we did not include the batch norm layer. So let's run this again, and then we now have this summary right here, which is exactly the same as that of our previously built model with a sequential API. And then now we want to fine tune our model, that is all these layers which were frozen, that is not trained. We now want to make them trainable. So right here we'll get back, and then we'll simply have backbone.trainable, and we set that to true. Then here we are going to set this trainable to false. Now recall when we were building this ResNet 34 model right here, we had this trainable parameter which we made use of. You remember here we had training, sorry, it's not trainable. Let's get back here. That was training. So we should have training here, not trainable. It's different from this one, so take note of that. This is trainable and this is training. So when we set this training to false, and we'll get back here, you would find that this batch norm took in this training parameter. And the reason why we need this specially for the batch norm is simply because the batch norm works differently during training and inference. And then during training, the batch norm layer normalizes its output using the mean and the standard deviation of the current batch of inputs. Whereas during inference, the batch norm layer normalizes its outputs using a moving average of the mean and the standard deviation of the batches it has seen during the training. So since at inference, or when we're fine tuning, we do not want the batch norm to take the current mean, or rather the mean and the standard deviation from the current batch of inputs. We are instead going to compute this from what it saw during training. And so that's why this training parameter is very important. We have this training right here. You see, it takes the input and the training, where we could set training to be false for training mode, and training to be true for training mode, and training to be false for inference, or let's say fine tuning. Now before we move on, you should note that this layer, the trainable set to false, is different from setting training to false. When you set a layer's trainable parameter to false, it simply means we do not want to update the weights when training. But when we set training to false, it means we're working in inference mode. In the case of the batch norm, this gamma and beta are trainable parameters. And so when we say layer.trainable equal false, it means that they are not going to be updated during training. But on the other hand, this mean and variance aren't trainable parameters. Instead, they are parameters which adapt to the training data. And that is why when we are at inference mode, that's when we set training to false, we do not want to disrupt the mean and variance values gotten during the training based on the training inputs. And so as we saw already, this mean and variance at inference mode will be simply the moving average of the mean and standard deviation of the batches it has seen during training. And so clearly these two concepts, that is setting the weights to parameters not to be trainable, and so clearly the concept of setting these weights not to be trainable is different from that of working in inference mode. Nonetheless, it should be noted that in the case of the batch norm, setting trainable to false on the layer means that the layer will be subsequently run in inference mode. Now, although we've seen that these two aren't, they don't mean actually the same thing. Now, also note here that setting trainable on a model containing other layers will recursively set the trainable value of all inner layers. And if the value of the trainable attribute is changed after calling compile method on a model, the new value doesn't take effect for this model until compile is called again. Okay, so that's it. We could check out the dropout. Here we have this dropout layer, which doesn't have any trainable parameters. But remember that the way the dropout works is that you have, let's say, some inputs. Let's take this off. You have some inputs, and then if you to pass through the dropout layer, at the end you have some of these inputs which will be not considered. So you have maybe this will proceed, but this not taken into consideration. Maybe this moves, and then this not taken into consideration. So the dropout of 0.5 simply means that half of our inputs will move forward and the other half will not be taken into consideration. And so you see that at inference, that is when we are actually trying to test our model, we do not need to drop out some of this neurons right here. And so generally the dropout also takes in this training parameter here, where when we set training to true, it means that we are in training mode, and so we could actually drop out some of these values. Whereas when we set the training to false, then we are in inference mode, and so we do nothing. So we just allow the inputs to pass without any modifications. And you could also see clearly from here that the layer dot trainable doesn't really apply because dropout doesn't have trainable parameters, whereas with this training we could decide whether it's true or false. That is whether it's training mode or inference mode. So in fact what we're saying is we have this model here, we have the backbone and we have the head for classification. We apply transfer learning by freezing all this. We freeze all our backbone, so no parameter here is updated during training. And then now we move on to fine tuning, where in fine tuning we want to update these parameters with a very small learning rate. And then we also want to avoid a situation where those mean and variance statistics which were gotten during the training process will be offsetted during this fine-tuning process. And so the batch norm is kind of like a special layer where even during the fine-tuning where we want, or where we have set the trainable to true, that is we want to update these weights during the training, we do not want to modify or offset the batch norms mean and variance. And so we are going to set this training here to false, so it still behaves as if it were in inference mode. So getting back here, we have our training which has been set to false, and then we could start training our model again. But one point to note here is we do the fine-tuning on a pre-trained model which has already been trained. So what we'll do is we're not going to start training this model this way. We'll start by training the pre-trained model. So we start by having this backbone to be set to false and this training set to false. So we're going to repeat the transfer learning process again before then applying fine-tuning. So each time you want to apply fine-tuning, make sure you have this set to false, training set to false, and then you go ahead. So yeah, let's run this again. Here's our fine-tuned model, which achieves best validation accuracy of about 70%. Okay, now we're done with transfer learning. We're now going to apply fine-tuning. To do this, we're going to set this to true. So all we need to do here is set this to true. We're not going to rerun this again. It's the same model, and that's even the idea. The idea is for us to start with the backbone which is not trainable, and then later on make it trainable, or while now just simply recompiling the model. So don't forget to recompile this model to take into consideration the fact that some parts of the model are now trainable. So let's get back here, recompile the model, and see what this gives us. Now as we start training, we notice that this validation accuracy here isn't looking like what we expect, because before getting to the fine-tuning, we already had a model with a validation accuracy of about 70%, but now we're getting this 33%. And the simple reason why this is so is because our learning rate here, we still maintain the same learning rate instead of reducing it before the fine-tuning. So we would have to stop this here, then we would get back to this here, set this to false. So we would have to start back the whole process, set this to false, and then we retrain the model. We get this accuracy of about 70%. Now we get back here and we set this to true. So we set this to true. That's fine. We run the cell, backbone now trainable, and then we are going to make sure this learning rate here we divide it by 100. So we're going to make use of a very small learning rate. Now once we have this, we're going to run this again. So we're going to compile our model and restart the training process. Training now completed. Here are the results we get. You could see that the validation accuracy increases up to 72.2%. so we make an extra gain of 2% for the validation accuracy after fine-tuning our model. And this makes sense since fine-tuning permits us to squeeze out some extra juice from this backbone, since this time around it's actually trainable. And that said, we've just completed a section on transfer learning. Thanks for getting right up to this point, and see you in the next section.